Hey everyone, it's Mr. Glover here, just about to start our next set of notes. So today we're going to start with chapter 7. There is 7.1. It is the first section, but it's a math lab, and I don't think it's something that we're going to be doing this year. If you want to, you feel free to do 7.1, but it's essentially discovering how the graphs of exponential functions work. And then the follow-up lesson is this, which is kind of the meat and potatoes, if you will, about how to actually graph these functions algebraically rather than using a graphing calculator. So we're going to start at 7.2. First thing we should talk about is what an exponential function is, and then we'll focus on how to actually graph those functions. So exponential functions are those that can be expressed in the form y equals a to the power x, where a is what you'd call the base, and a is a constant, and x is your exponent, but x is the variable. So let's go through a couple examples of what are and what are not exponential functions. Something like y equals 5 to the power x. That's an exponential function. Something like y equals 1/2 to the power x. That's also an exponential function. However, if we change where everything's written, if we were to write y equals x to the power 5, well, that's not exponential anymore. This is what you would call a quintic function. And something like y equals x to the power x. That is not an exponential function either, because we have a base that is a variable and an exponent that's a variable. I'm not actually sure what type of function this is, but it's definitely a pretty ugly function, and it's not going to be an exponential. So basically, if you've got a base that's a constant and an exponent that's a variable, you've got an exponential function. So let's start with the most basic one, y equals 2 to the power x. We're going to make a table of values and we're going to graph it, and we're going to use this information as a basis for the rest of our exponential functions. So essentially we're plugging -2 in where x is. So the first one would be something like y equals 2 to the -2, which is 1/4. If we do the same thing with -1, we'll get a y value of 1/2. 2 to the 0 is 1. 2 to the 1 is 2. And 2 to the 2 is 4. So if we go to graph this, we have x value of -2 and 1/4. We have -1 and 1/2. We have 0 and 1. We have 1 and 2. And we have 2 and 4. So our exponential function looks something like this. As far as the domain goes, you're not breaking any rules when you put something in an exponent. So you can have any x, so x is all real numbers. As far as the range goes, there is a restriction. You can never make 0 by putting an exponent on a number, and you can never make a negative by putting an exponent on a number. You can see that in the graph. So y must be strictly greater than 0 in this case. Exponential functions all have the same basic shape, but the steepness, and I don't think this is a real word, there's probably an actual word for this. The steepness depends on the base. Depends on the base a. For example, 3 to the x versus 5 to the x. Powers of 5 will increase faster than powers of 3, so 5 to the x would be a steeper graph. What about 1/2 to the power x? If we were to graph this, we would have the equation 1/2 to the power x which could be simplified to 2 to the minus 1 to the power x. So essentially, it's like 2 to the negative x. If you think back to other chapters that we've done, when you replace x with negative x, it's like flipping over the y-axis. So it's no different here. Essentially, this means we're going to reflect over the y-axis. And this graph is going to look the same, but it's been flipped. So instead of increasing, the graph is now going to decrease. What about minus 2 to the power x? If you were to graph this, you will find that half the values are positives and half the values are negatives. Anytime you have an odd power of a negative, it's a negative. Anytime you have an even power of a negative, it's a positive. So if we were to graph this, basically what you'd see is this pattern, this kind of spiraling pattern, oscillating between positives and negatives. So for simplicity's sake, we're not going to use negative bases. And what we're going to do is we're going to define this as non-exponential in shape. So we're going to impose a couple other restrictions. 1 to the power x is not allowed, and 0 to the power x is not allowed, and that's because they will both create straight lines. It's always going to be 1 or always going to be 0, so these are constant functions. Technically, they're both linear functions, because they don't have the same shape as an exponential. So we're going to sketch another graph. We're going to sketch 3 to the power x. We're going to need a table of values to do this, and then we're going to find the domain, range, x, y-intercept, and any asymptotes. So we'll start by making a table of values for x and y. We'll pick some values close to the origin, so we'll pick -1, 0, 1, and 2. 3 to the minus 1 is like 1/3. 3 to the 0 is 1. 3 to the 1 is 3, and 3 squared is 9. So if we go to graph this, -1 and 1/3, 0 and 1, 1 and 3, and 2 and 9, we get a shape that looks like, let's try that again. We get a shape that looks like this. It's very similar, but 3 to the power x is steeper than 2 to the power x. As far as the domain goes, we still can put any number in our exponent. So x is still all real numbers. The range, y is still greater than 0. You can't make 0 out of an exponent, so y is greater than 0. Our x-intercept is not applicable because it doesn't cross the x-axis. And as far as the y-intercept goes, the y-intercept is 1. And now, I haven't mentioned this yet, but you might have been noticing that they all seem to cross at the same point. If we look at any of these graphs, this one crosses at 1. This one crosses at, well, we don't know, but this one crosses at 1. This one crosses at 1. That all comes from the fact that any number to the power 0 automatically becomes 1. So every single one of these has a y-intercept of 1, unless we've gone and stretched the function vertically, and we'll talk about that shortly. Last but not least, the asymptote. There's no vertical asymptote here, but there is a horizontal asymptote, and it's at y equals 0. So far we have taken the graph, or taken the equation of a function and drawn a graph. Now we're going to go in the opposite direction. We're going to go from a graph to an equation. So to write an equation for a graph of a function, first thing you need to do is find the base. Assuming the function has not been translated or stretched, there's going to be two cases. The function will be increasing. So if the function is increasing, you will see the function go up as you move to the right. That means the base is greater than 1. If you want to find the base, find the y value at the point x equals 1, 1a, for example, this will be your base. If the function is increasing to the left, which means it's decreasing, it will look like this instead. It will start up high and it will decrease. That means the base is less than 1. And now there's two ways you can go about this. You could find your y value at negative x is negative 1, so that would be up here. Your base will be 1 over that y value. Or you could find the y value at x equals 1, and that equals the base. The only problem with this is it's going to be a little bit trickier for us to estimate 1/3 or 1/4 or 1/6 versus just finding a 4 and going 1 over 4. So I'll leave it up to you how you want to deal with that. But let's try a couple of problems here. The first one on the left looks like it's a decreasing function. So we could go to x equals 1. We could pick this point right here, and whatever that y value is our base, but I'm not 100% sure what it is. So instead, I can zoom in on this spot, and I know that when x is negative 1, y is 4. What that tells me is that y is 1 over 4 to the power x. The reason I know that is because it's decreasing. So it's a decreasing function. That tells me that the base is less than 1. So if I go to x equals negative 1, at x equals negative 1, y equals 4. So the base is 1 over 4. Similarly, we can do the same thing on this function, but the difference is that it's an increasing function, not a decreasing function. So I'm going to go straight to the point where x equals 1. It's increasing. That tells me the base is greater than 0. At x equals 1, y equals 5. And so I know that the base is simply equal to 5. That tells me my equation is y equals 5 to the power x. Just like quadratics, cubics, and quartics, we can translate, stretch, and reflect exponential functions in the x and y axis. The general rules are the same, but the equation looks different. It's going to look kind of ugly. This is the general form of any exponential function. Now, the letters don't really matter. It could be A, B, C, D, it could be K, C, D, H, could be whatever you want. But there's 4 variables that can affect your function. Y minus a variable will shift it up and down, just like before. C is going to be a vertical stretch, just like before. And anything in your exponent affects x only. So the things in your exponent are going to be either horizontal compressions, like D, or there'll be horizontal translations, like H. And there's some requirements that you can't have C equals 0 or D equals 0. As far as these go, K and C affect Y, while D and H affect X. So we're going to go through each of these parameters one at a time to see how they affect our function. C is going to be our vertical stretch. So this is a vertical stretch by a factor of C. Vertical stretch by a factor of C. If it's negative, if C is less than 0, then this will be a reflection over the x-axis. So for example, 3 to the power x is going to be the blue function. If we apply a vertical stretch of 4, like the red function, it's a steeper graph, and it changes our y-intercept to 4. If we apply a vertical stretch of -2, effectively it stretches it by a factor of 2, but it also flips over the x-axis, and we get a y-intercept of -2. If we change d, d is going to be our horizontal compression. So d is a horizontal compression by a factor of 1 over d. What that means is that anything that you put up here, you need to take your x values and divide by that number. So if this is a 2, well, that's going to compress it horizontally by a factor of 2. Divide all your x's by 2. If this number is a negative, though, remember, it's going to be a reflection, just like we saw with C. If we replace x with negative x, though, instead of flipping over the x-axis, we flip over the y-axis. So if d is less than 0, then this is a reflection over the y-axis. And we can see that in the graphs. The blue function is the original, 2 to the power x. If we replace x with 3x, 2 to the 3x is a steeper graph because we've compressed it horizontally. Think of like an accordion squishing it horizontally. If we replace it with negative 0.5x, it's not only a vertical stretch by a factor of 2, it's also a reflection over the y-axis. So that's why we see it is now decreasing and it's flatter. K, we'll go back up here. K is the variable being subtracted from y. So what that means is you're going to see a horizontal or a vertical stretch. You will see a vertical translation. Whatever you have for K is going to tell you how many units up that this has been shifted. K could also be on the other side, and it could be just a number being added to the end of our function. And just like every other function we've done, that's a vertical translation. So K is a vertical translation. K units up. And you see this here. The blue function, 4 to the x is the original. 4 to the x plus 2 is 2 units up. 4 to the x minus 3 is 3 units down. And last but not least, h. H is the variable inside the brackets with x. It's going to be a horizontal translation, and h will shift the function left or right. So h is a horizontal translation, h units right. So 6 to the x is our original function. 6 to the x minus 3 has been shifted 3 units right, and 6 to the x minus 2 has been shifted 2 units to the left. So we're going to take a function. We are going to transform it in a couple of different ways, and then we're going to graph the corresponding functions. The original function is y equals 3 to the x. And we already have a table of values for 3 to the x, but I suppose we should do another one. I'll just write it up at the top here. Y equals 3 to the x. It has an xy table that looks like this. X is -1, y is 1/3. When x is 0, y is 1. When x is 1, y is 3. And when x is 2, y is 9. I guess we should have another one. We'll go 3 and 27. Okay, so we're going to go and transfer this information over to this table. It's going to seem kind of weird, but what we're doing is we're writing the x, y coordinates for every point rather than a separate table of values for each transformation. So -1 and 1/3 is this first point. 0 and 1 is the second point. 1 and 3 is the third point. 2 and 9 is the fourth point, and 3 and 27 is the fifth point. Okay, so now we've got to think about what's happening with each of these transformations. The first column, 2 times 3 to the power x, this is going to be a vertical stretch by a factor of 2. In other words, take all your y values and double them. So the x values are going to stay the same. They're still -1, 0, 1, 2, and 3, but the y's are now doubled. 1/3 becomes 2/3. 1 becomes 2. 3 becomes 6. 9 becomes 18. 27 becomes 54. So we've gone and we've applied our vertical stretch. Now we've got to apply the last translation, or transformation, which is a translation. If x gets replaced with x minus 4, effectively what we're going to do is we're going to translate 4 units right. Horizontal translation, 4 units right. Effectively, we're going to be adding 4 to all of our x's. So the y values are the same. The y values are 2/3, 2, 6, 18, and 54. But the x's are now 4 greater. Minus 1 plus 4 gets us 3. 0 plus 4 gets us 4. 1 plus 4 is 5. 2 plus 4 is 6. 3 plus 4 is 7. So now we have a new set of points. These points are going to be our transformed graph. We'll draw the original. We'll draw the original in, let's do them in very different colors. So the original will be in pink. And it was the points minus 1 and 1/3, 0 and 1, 1 and 3, 2 and 9. So this is what the original looks like. The transformed one, which we will do in blue, has the points 3 and 2/3, 1, 2, 3 and 2/3, 4 and 2, 5 and 6. I think that's as far as we can go. So they're similar functions, but this one is steeper and it's been shifted over to the right. Increasing or decreasing, it's increasing. The domain, all real numbers. X can be anything. The range, though, y is strictly greater than 0. The asymptotes, y cannot equal 0. So y equals 0 is a horizontal asymptote, and the 0 is not applicable. And now you might be asking, what's the y-intercept? It used to be 1. Well, what's the new y-intercept for the blue function? In order to find it, we are going to have to plug x equals 0 into our equation. If we do that, 2 times 3 to the 0 minus 4 gets us 2 times 3 to the negative 4, which is 0.025. Which is close to 0, as we would expect. Okay, so we've gone through graphing from a function. We've gone from a function's graph back to the function. Now we're going to use these to solve some problems. So exponential functions of the form y equals a to the x, where a, is greater than 1, can be used to model exponential growth. Exponential growth would be something like a bacteria multiplying. It would be something like population increase. It would be something like increasing your money when you have an interest applied to a savings. It's anytime something grows rapidly where every time the increase is greater than the previous increase. Exponential functions where the base a is between 0 and 1 can be used to model exponential decay. And an example of exponential decay would be like a half-life. Think about chemistry class or science 10 when we talked about half-lives. This is exponential decay. And we're going to go through how to actually do those problems now in their full glory, rather than kind of taking some shortcuts by just multiplying by 0.5. The half-life of an unstable element refers to the length of time required to spontaneously decay to 1/2 of its original mass. So basically, these unstable isotopes are going to break down and decay into something more stable. We know through testing that half of the element will decay after a certain period of time. So we can essentially figure out how old something is by measuring how much of the radioactive isotopes are left, and we can figure out how many half-lives have passed to get down to that point. So the radioactive, or a radioactive sample of radium-225 has a half-life of 15 days. The mass m in grams of radium-225 remaining over time t in 15-day intervals can be modeled using the exponential graph shown below. What is the initial mass of radium-225 in the sample? What value does the mass approach as time passes? And what are the domain and range of the function? So the initial mass is going to be whatever the mass is when time is 0. So at t equals 0, we have a mass of 1 gram. What value does the mass of radium-225 remaining approach as time passes? Well, after 1 half-life, we're down to 1/2 a gram. After 2, 0.25. After 3, 0.125. It's pretty clear that this is getting closer and closer to 0. So as time approaches infinity, our mass is going to approach 0. It will never reach 0. I mean, technically it will, but the decay slows quickly. You'll go from losing 1/2 a gram to losing 1/4 of a gram to losing 1/8 of a gram to losing 1/16 of a gram to losing 1/32 of a gram. So essentially every time you increase your half-lives, you're losing less and less and less, to the point where you might have 4 atoms left, and that'll turn into 2 atoms, and eventually 1 atom, and then eventually 0. But we're talking about orders of magnitude that are so large, we're effectively not going to see them reach 0 in our lifetime. And question C, what is the domain and range of this function? Well, it looks like our domain goes anywhere from 0 and up. We can't have negative time. So x is greater than or equal to 0. I guess t, we should probably call it t because it is time. And as far as the y value goes, well, the mass is somewhere between 0 and 1. So mass is between 0 and 1 gram. Write the exponential decay model that relates the mass of radium-225 remaining to time in 15-day intervals. All right, so this is where we actually make an equation that matches this. Now, we're going to follow a simple system for this, and we will write many of these decay models. The basic idea for all of these functions is that y is going to equal some initial amount, call it a naught, and it's going to be times by the base of our exponential function. If it's growing, the base will be positive and greater than 1. If it's decaying, the base will be positive, but between 0 and 1. Since this is a half-life, our base is going to be half because we're losing half every time. So it's going to be 0.5. And then there's going to be some exponent, we'll call it x. For this question, though, we've got a couple of options. We could simply write our mass as 1.0 times 0.5 to the power t. If we choose to do this, then t is going to represent the number of half-lives. because after one half-life, you decay by 50%. After two half-lives, you decay down to 25%. If we wanted to model this using days rather than number of half-lives, it's a simple fix. It's still m equals 1.0 times 0.5 to the power t, but instead of just t, we divide by 15. If we do this, then t represents something different. T is going to now be the number of days. And the reason why is we're dividing by 15. If we have 15 days divided by 15, that's 1. That's equivalent to 1 half-life over here. So it's a minor difference, but it depends on how you want to actually model the question, whether you want to model it in terms of half-lives or in terms of days. So now estimate how many days it would take for radium-225 to decay to 1/30th of its original mass. And I wish I had a little more room here, but unfortunately we don't. We can zoom in though. So we are decaying to 1/30th. So if m equals 1 times 0.5 to the power t, and we're decaying down to 1/30th, so this is 1/30 equals 1 times 0.5 to the t, then effectively 1/30 is 0.5 to t. The 1 will go away. There's a couple of ways that we can go about solving this. We can do it using guess and check. We can solve this using a technique called a logarithm, but we haven't done that yet. So I'm going to say guess and check is probably our best method. Another way to do it, if you can't recognize 1/30th, is we can use some exponent laws to simplify this a little bit further. All right. 0.5 is like 1/2. So 1/30 equals 1/2 to the power t. Okay. Now, when we exponentiate a fraction, both the top and bottom receive the exponent. So 1/30 is going to equal 1 to the t times over 2 to the t. But 1 to any power is still 1. So we can kind of disregard that t, and we can write this as 1/30 equals 1/2 to the power t. Now that we have it like this, one fraction equals another fraction, we can flip the fractions upside down. And we can write 30 equals 2 to the power t. Now it's going to be much easier to estimate. We just have to try powers of 2 until we get close to 30. So we could go, well, I know it's not 2 to the 2. Let's try 2 to the 3. 2 to the 3 is 8. 2 to the 4 is 16. 2 to the power of 5 is 32. So it's very slightly less than 5. We could try 2 to the 4.5. 22.6, it's not quite enough. Let's try 2 to the 4.8. 27.9, getting closer. 2 to the 4.9, 29.9. That's as close as, well, we can get closer, but that's close enough for now. So t is going to be approximately 4.9 days. Now we've got to convert back to half-lives. So 4.9 times 15 days per half-life gets me 73.5. So time is approximately 74 days. We could have used the other equation, but the problem is we would have had a fraction in our exponent, and then to solve for t would have been a little bit more painful for us. Okay, we're almost done. One more question. The growth of the internet can be measured by the number of computers offering information. These are called hosts. In 1995, there were about 7.4 million hosts. Number of hosts n million at any time t years after 1995 can be modeled by the function n equals 7.4 times 1.59 to the power t. So we have three things we've got to do with this function. We've got to first graph it. We're only graphing it from 0 to 20. we need to estimate the number of hosts in 2010, and then we have to estimate in which year did the number of hosts reach 1 billion or 1,000 million. So for part A, we can use the graphing calculator or we can use Desmos. That's what I'm going to use. So we're going to sketch this graph from 0 to 20. I'm going to go over to Desmos, and I've got the function y equals 7.4 times 1.59 to the power x. If I go ahead and graph this from 0 to 20, we are going to reach, we're not going to reach 20 for a long time. We're not going to reach 20 until about here. So like we're in the thousands now. So it's a very, very rapidly increasing function. Goes almost straight up if we're going from 0 to 20. And we won't be able to see 20 unless we change our scale to be very, very, very large. So if we're going to graph this, from 0 to 20, our graph is effectively going to look like this. If we wanted to draw it from 0 to 20, and we wanted it to look, to be completely contained in this grid, we could do that, but we would have to make each of these squares worth like 200. And at that point, we're not really representing our data very well. We need to recognize that it's a steep increase, which is why I graphed it like this. Part B, to the nearest million, estimate the number of hosts in 2010. So in 2010, we are 15 years after 1995. So 2010 minus 1995 equals 15 years. So effectively, since t is years after 1995, we can just set t equal to 15, and we can calculate how many hosts are there when t equals 15. On a graphing calculator, you can do this by inputting your function in the y equals menu, and then going to the calculate menu and just hitting value. And you can just type in 15 for x. Or on Desmos, we can try and find out what y is when t equals 15. It's going to be a little bit tricky because this is such a large graph, but I can use a trick. I can type in x equals 15, and I can try and find the intersect of these two. So now I've got a vertical line at x equals 15. I'm going to change my scale a little bit because it's very hard to see. So we're only going to go from 0 to 20. Whoops, we're going to go from 0 to 20. Okay, and I'm going to increase the steps in the y direction. I'm going to make every square worth like 100. Oops, maybe that's not going to work. Maybe I will just change my my y-axis to go from 0 to, I don't know, 10,000. This is one of those times where the graphing calculator might not actually be much more difficult than Desmos. So this is what the graph looks like. I want to find the intersection, so I'm basically finding the point where this graph equals or has an x value of 15. The intersection point here is 7,765.8. So 7,766 is going to be our answer. At t equals 15, n equals 7,766 million hosts. All right, one more question, part C. In which year did the number of hosts reach 100 million or a billion? Okay, so this is going to be one of those ones where we make two functions and we make them intersect. One function is going to be 7.4 times 1.59 to the t. So make y1 equal 7.4 times 1.59 to the power x. We're going to make y2 equal to 100 or 1,000 million or a billion. Since y is going to be in number of million, n million, we need to make n equal to 1,000. And we just have to remember that 1,000 actually represents 1,000 million, not 1,000. So what we're going to do is we're going to graph these two. We will graph and find the intersect. So we go back to Desmos. We've already got the top function, but this one now has to be 1,000. Find the intersection point. Y equals 1,000 when x equals 10.58. X equals 10.58. Y equals 1,000. So 10.58 years later, n equals 1 billion hosts. I guess we should probably actually add 10.6 years back. So this would be partway through 2005. Slightly halfway through the year. So that's where we're going to end the notes today. We've gone through a lot of stuff. We've talked about graphing the functions, graphing exponential functions from the equation. We've gone from the function making the equation. We have taken these functions and we have applied them to real-world problems, and we're modeling exponential growth and decay using these functions. So that's where we're going to end the notes now. These are some problems for you to try. Page 403, 3 to 5, and 7 to 10. The starred questions will be, I guess we could call them bonus. They're just extra problems, extra things that you can try that will be similar to what you'd find on a test. But this is all you really have to do are the bolded questions. I would recommend the others, but they're not mandatory. So I'm going to end the notes here. Hope everybody has a great rest of the day, and I will see you all on Monday in our Zoom meeting. All right, take care. Bye for now.